Yeah, so we were in the middle of discussing the Shinui Mara, and we explained this diagram here. So I want to finish explaining this, and then I'll try to give you a certain idea what to do to visualize it with the three-dimensional. But this is really, really very good. So just first focus on the left side. This line here represents the ecliptic. The guy is standing in front of the computer, just like you're watching this right now, and he's viewing at this page. This page is the western, he's facing the western horizon. This is where the heaven touches the earth, this line. And if you take a look at the western horizon, so the left side will be south, the right side will be north. Now, the guy is facing western horizon, and he sees this. Imagine that there is a line in heaven that represents the Mazolos. So if Tele is right now on the horizon, then the ecliptic is very steep. We explained that previously, that depending on which mazel touches the horizon, that's what the angle, the Netias Hamilke is. We even gave a chart. I think I have it here. This shows for different values of celestial equators on the horizon. So we see if Tele, that's 0, then it's 83. Let's get back to this picture. Okay. So this is we showed already that. So this is the most it can be is 83 degrees. This angle is 83. Now, take a look here. Try to focus on this one here. M is where the moon is visible for somebody that's not for the imaginary person that's standing in the center of the earth. However, the person that's on the surface of earth, for him the moon is a lower, a straight line. It's a directly straight line. It's lower on the horizon. That's the idea. It goes. It's visible for him instead of here. So it basically lowers. According to calculations, it's here. It's on the same azimuth. It's just lower on the horizon by him. Right? That's the only thing that changes. It's like he takes a line from his zenith point and he draws it all the way till the horizon. So for somebody that's in the center, it's visible 5 degrees above the horizon. Somebody that's on the earth, it's on the horizon itself. So it just gets lower on the horizon, but on the same azimuth point. I never used the word azimuth yet, but azimuth is the same idea, the same concept. There's altitude and azimuth. When you drive a car, you see what azimuth is. It's you take your horizon, you divide it into north, south, west, east, and northeast, east, northwest, west. So it's like a line that's going directly from here to here, and that's called the azimuth line. It passes the top of his head. So what we see is that the effect of Shinui Mara changes just the height of the horizon. It's the same azimuth. The calculations give us that the moon is here, but in actuality, we must lower this a little bit for the Shinui Mara and lower it a few degrees, actually 1 degree. This is the most it gets. 1 degree, we lower it, and that will give us the real place where the moon is visible. So here we did it. We took the moon, this is the horizon. We drew a straight perpendicular line from M to M prime. That means that's how much it gets lowered. for somebody that's standing on Earth. And now we want to know what is the new value of the moon that's visible for somebody that's on the surface of Earth. What's the new oirech and the roichav? So you see, take a look at this tiny triangle here. MB. MB is the amount of shini oirech. It changed. Now it's visible here. So we draw a line perpendicular to B. That's the roichav. It changed roichav and oirech. The oirech is MB, and the roichav is B M prime. Shini roichav is B M prime. Shini oirech is B M. So this MM is the hypotenuse of the triangle, and it caused two effects. It caused the MB, Shini oirech, and BM prime, Shini roichav. So the new spot, in order to know the new spot of the moon, we must find out what's MB and deduct it from the oirech rishon. That would be oirech sheni. And also, you must deduct BM from the roichav, because right now the roichav was 0. The roichav was on the ecliptic itself. And this is it doesn't matter really if it's. I made it a simple case, but you can figure out yourself that the same thing applies if it starts off initially with the roichav. The same triangle happens, and then we deduct BM prime for the roichav. This is a situation when it's when teleh, it's 83. How about, look at this. This is when it's Znaim. When Znaim is on the ecliptic, take a look here. You see how it is by 180. When 180 is, when the celestial equator is 180, then we have 34. That's the lowest possible. This angle here is 34. Then look what happens. The shini oirech, the same story. So M goes down M, same amount. This is how much it goes down the horizon because of the shini mar. It always goes, as I said before, perpendicular to the horizon. It goes down straight, perpendicular to the horizon. That's shini mar. But what effect does it have on the longitude and latitude? Let's see. Again, let's draw a line. BM. Ooh, became very big. The roicha became big. The oirech, however, BM, not prime, plain BM is not so big. So this is when it is. We can see the rhombus inside all the numbers. This gives you a general idea that when Teleh and Shoyer on the horizon, there is a huge shini oirech and a tiny shini roicha. When Meznaim is on the horizon, then there's a big shini roichav and a small shini oirech. Now I wrote here that the formula is about one. It's not 1 degree; it's a little bit less. 59 chalakim times sine the ts milka. It's just for somebody who wants to know the math behind it. Or 1 degree times cosine the ts milka. That's for shini oirech, and for shini roichav, it's 1 times sine the ts milka. Now, there's a few remarks I want to make here, just for people that want to understand things a little bit better. So you can get yourself a globe for 99 cents, or for maybe $1.50, the sharpener, and you can simulate the thing very clearly to understand what shini oirech roichav is. You take this globe, you take it out from the white. It comes with it's like a sharpener. So you just hold in your hands just the globe. You don't need anything else, just the globe. Now imagine that the equator that would be now the ecliptic, the Galgal Mazalis. Use your imagination. You're not interested in having a world now, you're not interested in an equator. You want to have that, what's on the globe called equator, that's the Galgal Mazalis. Also, the lines that are called latitude are going to be the Roichav HaYereach, the latitude. Now, take this globe, this whole thing, and try to find a certain cup or a certain pot or a glass that should be, half of that should sink inside the glass and half should stick out. Try to find something a size. So, the part that is above, that's the part of the ecliptic, of the Galgal Mazalis that's seen for you in a certain place where you are. Now, make sure that make the globe in such a manner that the celestial equator, that's called ecliptic, should have a very steep angle towards the horizon, towards you're putting it into a glass jar, so that it should be that circle that represents the ecliptic should almost be a 90-degree angle towards the horizon. Now, what is so now take a magic marker and mark above the glass a certain point on the ecliptic. Mark it there. That is where the moon is for somebody that's standing in the center. In the center. Now, it's a little hard to imagine because you're having a tiny globe. But imagine then there is another ball inside that ball. So, for this, just believe the fact that we tried to show before, that for a guy standing on the surface, this object appears 1 degree lower on the horizon. So, how do you do that? You take a tiny thread and you let it hang loosely from the point that you marked with your magic marker on the ecliptic. You take that thread, you let it hang loosely. What will you see? Now, when you let it hang loosely, automatically that goes directly perpendicular to the horizon. That means this is the amount that it gets seen lower on the horizon for somebody standing on the surface of Earth. It gets seen a little bit low on the horizon. But the effect of this, the seen lower, it has an effect on the longitude and on the latitude. The new point where where the moon will be seen, that means the end of the thread. You stick in the thread at the point where you marked, and now you have the second end where it points now, will be lower in the longitude and the latitude. Make a change on both. And this change of longitude and latitude depends on how steep the angle of the ecliptic toward the horizon. Play around with it, you understand what I'm talking about. So this is the idea of Shinui Mara that the Rambam talks so nicely and he explains, and I'll say it in the next year more detail. The Rambam gives you numbers for every single point of the ecliptic, but that determines the inclination of the ecliptic towards the horizon, and that in turn determines the Shinui, Oirech, and Roichav. Because as we said, the more we showed here also, the more it's inclined, the more the Shinui Roichav and the less the Shinui Oirech. So this is the idea of this whole thing of Shinui Mara, and hopefully the next lecture we can go into the Rambam inside. Thank you for listening.